Okay, so today I'm going to work 2010, the AP Physics C Mechanics free response question for with rotation and rolling. So we're going to start with the picture, which we can see that something is rolling downhill. It then rolls off and hits a car or a cart that is sitting at the bottom of the hill, and we have the vertical distance of 3 meters and we don't know how far it's gone. Alright, the bowling ball has a mass of 6 kilograms is released from the top of the slanted roof that is 4 meters long and angled at 30 degrees as shown above. The ball rolls without slipping. The rotational inertia of a sphere of mass m and radius r about its center mass is 2/5 mr squared. Now, before I go any further, I can see that I is 2/5 mr squared. So I'm going to go ahead and calculate that. 2/5 times 6 times r squared. Well, I don't know what that is, so I'll just leave that as is. I thought I was going to be able to calculate it, but I don't know the radius of the ball. So on the figure below, they want us to draw and label the forces that act on the ball at their point of application as it rolls along the roof. The first force that I always think about is gravity. Gravity is always the first force on my mind, so that's the force of gravity. Make sure here you don't make the mistake of writing just little g. Make sure you write the force of gravity. Now, of course, there is a normal force, and normal force is applied from the surface that it's on. So my normal force actually looks like this. And then there's one more force. This wouldn't roll if it weren't for friction. So there's my frictional force that's acting. Those are the only three forces that are acting on this as it is rolling down the hill. So that is the end of my free body diagram. A little bit weird for free body diagrams. We're used to the dot and we have all the arrows, but again, this is how we have those going. Now it says calculate the force due to friction acting on the ball as it rolls along the roof. If you need to draw anything other than what you've shown to assist your solution, use the space below. Do not add anything to the figure. So they're telling you don't draw components of forces. And they want to know what that force due to friction is as we're going down this roof. So I'm going to redraw that free body diagram. I'm going to draw it again. I'm going to draw gravity. I'm going to draw normal. And I'm going to draw friction. Okay, now, you know, we could go back to the old days and say friction is fun, but we can't do that because we don't have mu, so there's no finding that. So I go, well, what can I do? Well, I can look at this and I can say, well, friction and gravity, if I do net force, so if I say net force, well, which way is this going to accelerate? It's going to accelerate down the hill. So I'm going to do the down the hills minus the up the hills. The down the hill is a component of gravity. Now the hill was inclined at 30 degrees, so this is 30 degrees. So this would be mg sine 30. So this is going to be force of gravity in the x direction minus the frictional force, which is backwards. So ma is equal to mg sine 30 minus friction. Okay, but I'm kind of stuck at that point with, I don't have the acceleration, do I? Let's look. No, I do not. So since I don't have the acceleration, I can't finish this out with this. I can do this much. I can say 6a is equal to 6 times 9.8 sine 30 minus friction. And so I can do that. I get 6a is equal to, let's see, that'll be 29.4 minus friction. So I have an equation where I could find friction, but I would need a to do so. So I say, okay, well, let's see. What if I go and I try to find the acceleration? Maybe I can do that. So this thing accelerates down the hill, but it does so because of gravity and it rolls because of torque. So torque net is I alpha. Torque is also RF sine of the angle. What's the only force that's causing this to roll? The only one. The axis of rotation is in the middle. Normal and gravity go through that, so they exert no torque. The only one exerting torque is friction, and it's located at a radius r times the frictional force times sine 90 is equal to I is 2/5 mr squared times alpha. Now, alpha is not A. I'm going to go ahead and get rid of an r here and an r here. And I know that acceleration is alpha r. So alpha must be acceleration over r. And so I'm going to use that. Sine 90 is 1, so that can go away. So I get friction is equal to 2/5 mr times A over r. And what happens to my r's? They go away. Good thing, because I didn't know r. So good thing they went away. So now I have this. So friction is 2/5 times my mass, which is 6, times A. Or friction is 12/5 A. Well, now I've got two equations for friction. I don't want acceleration, so I'm going to solve this one for acceleration. So acceleration is going to be 5/12 friction, and I'm going to plug that in here. So friction is 29.4 minus 6 times that acceleration, which is 5/12 friction. Now I can do a little math on this. So I get friction is equal to 29.4 minus, and that's 30 over 12, 2.5 friction. Now I'm going to add that 2.5 friction to both sides to get 3.5 frictions is equal to 29.4. Divide by 3.5, and I get friction is equal to 8.4 newtons. And there is my frictional force for that. So that was part, what, B? Yeah, that was part B. Okay, so we had to do a little finagling. This is, again, this is how we created the original equation for what is the acceleration of an object going downhill when we did that. But it also applies in this. Okay, part C. Calculate the linear speed of the center mass of the ball when it reaches the bottom edge of the roof. So we want to know how fast is it going right here, and we want to know what is that linear speed. Well, anytime that I see something that goes from a high position to a low position, my mind automatically goes to conservation of energy. If I can use conservation of energy, I'm going to, because energy is pretty true to everything that I ask of it. When I go to do energy, it works, and so that's what I like. So we're going to do energy. So at the top of the hill, up here, it's all U, because it says it's released from rest. So your V equals 0, so your K equals 0. Down here at the bottom, if I consider this, if the H is 0 right here, then U is 0, and this is all K. So I'm going to start with a K naught plus a U naught equal to a K final plus a U final, but I know that this is 0 and this is 0, so I'm really doing a U naught becoming a K final, a conservation of energy from that potential energy to that kinetic energy. And U naught is mgh, and kinetic is 1/2. Now we got to pay attention because this is rolling, so we're 1/2 mv squared plus 1/2 I omega squared, because remember that we are translating and rotating both. So we need to have both of those in our kinetic energy equation. So I'm not adding a new thing. These two in total make up the final kinetic energy. So let's plug what we can. So I know that this hill is 4 meters long and this is 30 degrees. So this would be my height, which will be 4 sine 30, which is 2. So my mass is 6, my g is 9.8, my height is 2, is equal to 1/2 times my mass of 6 times the velocity plus 1/2 times that I that I had a minute ago, which was 2/5 times 6r squared. Okay, if you're wondering where did she get that from, that was from this, the 2/5 mr squared, and I just put the 6 in there as my m, and so there we go. Now I got to put my omega in here. Now, over here on the side, I'm going to put a little star. Okay, one of the most used relationships in physics or in rotational physics is the fact that V com is equal to R omega, and omega would be V com over R. This is so common, and I'm going to plug that in into instead of omega. Why am I going to do that? Because I want V com, so I want everything in terms of V com. If I leave that as omega, I've got two variables, but if I can put this in as V com over R, then now I'm left with V coms. Okay, at this point I can do some canceling, and I'm going to get a different color pen for just a second here so that it stands out. Didn't have this at the ready. Okay, so that I don't have to do so much arithmetic, I see a 6 here, here, and here. Now remember, they have to be in everything to make them go away. So like if it was in this one and this one but not this one, I couldn't. But because it's in every single one, I can make that go away. I see a 2 here on the bottom and a 2 on the top, so I'm going to go ahead and get rid of those. I have an r squared here. This r is getting squared, so it's going to be an r squared on the bottom, so I'm going to get rid of that and that. Be careful, don't get rid of the squared, because it also goes with the V com. Okay, so let's simplify this a little bit. We get 19.6 is equal to 1/2 V com squared, plus I end up with 1/5 V com squared. Now I need a common denominator, so 19.6 is equal to, I'm going to go with 10, so I get 5/10 V com squared plus 2/10 V com squared for a total of 7/10 V com squared. Now I'm going to multiply both sides by 10/7, and I'm going to get 19.6 times 10/7, 28 is equal to V com squared, and then I'm going to take the square root, and so I get V com is equal to 5.3 meters per second, and there that is. Now, I could have gone through and done this part of the problem first, use that to find an acceleration, then go back and find friction in part A. So there are multiple ways to go about these problems where I can do C before B, or B before A, or something like that sometimes. But in this case, this is how I'm going to do this. But there is another method. You can use conservation of energy to find this final velocity. You can then use that to find the acceleration, and you can work your way back to friction. Okay, so that's the linear speed of my ball as it reaches the edge of the roof. So the last question is, they say, okay, we're going to add something else to the problem. There's a wagon containing a box at rest at the bottom of the incline, and the ball is going to fall a vertical distance of 3 meters before it hits it, and the total mass of the wagon in the box is 12 kilograms. Calculate the horizontal speed of the wagon immediately after the ball lands on it. So I see a conservation of momentum problem going on. Okay, I see projectile motion So I see projectile motion, and I see a collision. So therefore, I see conservation of momentum. Anytime I see a collision, that's what I'm going to go with. Now, they asked me for the horizontal. Now, I know that when my ball leaves the roof, my ball is leaving like this, okay? Which this angle here is 30 degrees, so that makes this angle here 30 degrees because alternate interior angles are congruent. So my final velocity is 5.3 meters per second, and that has components. It has a Vx and it has a Vy. This one will be 5.3 sine 30, which is going to be 2.65. This one is going to be 5.3 cosine 30. No, I got those backwards. My bad. Look at that. This will be 5.3 cosine 30, and this one will be 5.3 sine 30. See, sometimes even the best of us make mistakes there. So 5.3 cosine 30. Luckily I caught myself before I got too far. So I get 4.6 meters per second. Okay, so these are my velocities when I leave the thing. Now the thing is that my y velocity is not going to matter. I'm not going to be concerning myself with my y velocity because this collision happens, and when this collision happens, we're only concerned with the forward momentum, or the forward motion, excuse me, of the box, because they only want to know the horizontal speed of the wagon. So I really only need the Vx, which is 4.6 meters per second. So I see projectile motion, but I really don't need it because I'm not looking for how fast is it going at the bottom. If I did, this one would be important. This is the only one that matters. So when it hits, horizontally, what I see is M1 V1x initial plus M2 V2x initial becomes M1 plus M2 Vx final, because they're going to hit and they're going to stick together. So this is the ball, this is the wagon, and this is the ball plus the wagon. So the ball has a mass of 6, and it is traveling horizontally at 4.6. I almost wrote the wrong one down. And this is 6 kilograms. I usually leave units off just because they can get really messy in there. Just make sure everybody's in the right units when you start. Mass 2 is the cart. What do we know about the cart? It's 12 kilograms, but it's not moving. And then in the end, we have the ball plus the wagon moving at Vx final. So I end up with, what's that, 27.6 is equal to 18 Vx final. So we're going to divide that by 18. And I find that my final velocity is 1.53 meters per second. And that's the final velocity of my cart.